let's go ahead and get started. Welcome to class. Okay, so big day, guys. We are finishing up our series on the ANOVA today. And hopefully today will be, again, just quite easy because it's actually just really repetitive to what we've been talking about for the past few weeks. It's the same story over and over and over again. So we'll go briefly through mixed designs, and then we'll talk about how to do the mixed ANOVA in SPSS, and then we'll just go through a brief review, kind of tying this all together. So bringing this back to that general linear model that we talked about several weeks ago, going through how what we're talking about today relates back to what we talked about in these, over the past several weeks. Okay, so to get us started, go ahead and do today's woo clap. What is the benefit of adding more factors to your model? Let me know what you think. Okay, so what is the benefit of adding more factors to your model? Why do we want to add more variables to your model? And I'm seeing some really great answers here. One of the big ones is that it can help explain some of the variance in your model or in the data that can improve the accuracy of your model. That's really it, right? If we are adding variables to our model, and assuming that they are variables that are significantly or meaningfully related to the outcome, this is going to help explain some of the variance. It's going to help account for some of the variance we have in the data, which means that we're going to have more variance in the data that is systematic to at least some of the variables in our model, and less variance that is unsystematic, that is unexplained. So when you add more variables to your model, whether we are talking about a multiple linear regression and we're adding in continuous and maybe categorical variables, whether we're dealing with an ANOVA and we're adding in more IVs, right? Whether it's between subjects, within subjects, mixed, doesn't matter. If we're adding more variables to our model, you can think of this as eating away more at that pie of the total variance. So more of that total variance becomes grouped under the variance that can be explained by your model. With the caveat, of course, that the variables you add should have a meaningful, i.e. statistically significant, relationship to the outcome. If the variables are not significantly related to your outcome, then it's not going to help explain more of the variance, obviously. So assuming you're adding variables that have some meaningful relationship to your outcome, the more variables you add, the more it's going to help explain variance in the data. And this is going to reduce the amount of unsystematic variance you have in your data. And thinking about our F ratio, the F ratio is simply systematic variance over unsystematic variance. So the more variance, the more that total amount of variance that we can explain, the more likely it is we're going to get a significant F ratio. We're going to be able to explain more of what's happening in our model. So having more variables in your model, having more factors in the model is a good thing if they are significantly related to the outcome. Now, you guys have also seen that we don't want to just add variables and as many variables as possible, right? Because the more variables you add, the more degrees of freedom it takes away, right? So we do lose power. So we don't want to just throw in every variable that we have. We do want to be a bit systematic in the variables we choose to add. If you're adding a variable that can only explain 0.5% of the data, that may not be worth the cost of the power to add it in. So do be thoughtful about which variables to add based on how much increase in explanatory value do they give you. And again, think back to our lecture on hierarchical linear modeling, where we add variables one at a time. And we talked about this idea of incremental validity. We want to see whether adding additional predictors to the model gives us a significant improvement in the explanatory power of the model, right? That's the R squared. If the explanatory power of your model doesn't increase significantly, there's no point in adding that additional variable because you're just costing yourself power without getting the benefit of increased explanatory power. So more variables can be a good thing by giving us more ways of explaining variance in the data. Just be mindful about the cost of power to your analysis by adding variables to it. So you don't want to add just any variable. You want to add variables that make sense, that are useful for testing your hypothesis. Good. So I see lots of really good answers here, right? So they can help explain variance, right? Explains my variance, yes. Can help account for more of the error, absolutely, right? Improves the predictive power, yes, definitely. Helps control for extraneous variables, yeah. So this can, having other variables can also just, in our research design, help us control for various kinds of possible confounds. So that's another reason why we might want to include these kinds of variables. Good. Oh, I was at the bottom. Okay. Yeah, increase prediction. Reduce type 1 error. I don't know if this is necessarily going to reduce the type 1 error, but again, this does help improve the prediction accuracy of your model. It does help you get a more, I guess, comprehensive model. Yeah, we can look at interaction effects. So assuming we are doing multiple IVs, we can look at how these different predictors or how these different IVs interact together, which can help us explain things that are much more interesting than looking at each variable by itself. Okay, so one of the things I want to emphasize today is that if you predict only main effects, we talked about this already, right? When you think about factorial ANOVAs, I have a main effect for appearance, I have a main effect for job. And if I don't think that these are going to interact, I should just analyze these separately, right? If you don't think there should be an interaction, then including them in the same model is, again, just going to reduce the power. Now, the reason, it would be odd for you to honestly include both of these without thinking there's an interaction. Generally, when we include multiple variables in our models, there are two big reasons for doing so. One, we want to control for things. So if you think about, again, that hierarchical linear modeling, and we have variables that might be included in step 1 to control for variance that we know is relevant to these variables, but not what we're really interested in. Right? So we want to include demographic variables. We know that a person's age, gender, income, education, right? That this can explain a certain amount of variance in the data. It's not what we're really interested in terms of our research question, but we know it's relevant. So we include those variables in our model to account for the variance that can be attributed to those demographic variables. So that's one reason why we might want to include variables. We want to control for various things. We might want to control for various confounds. Another reason to include additional variables is to account for more variance in the data that is interesting to us. So either because of the main effects or, importantly, because of the interactions. We think that variable 1 is going to interact with variable 2, and this is not something we can observe if we were to analyze variable 1 and variable 2 separately. We analyze them together because we think the product of these two variables will give us something above and beyond what we would get if we were to look at these things individually. So interactions are really important. Generally, if you include multiple variables in your design, it's because you're looking for an interaction. It would be a bit of a red flag, and people would raise their eyebrows a little bit if you have a design for an experiment that you're only predicting main effects and you're not predicting an interaction, because then you're just costing yourself in power without really gaining anything in terms of the explanatory value of those two variables together. So interaction effects are important. This is something that's really interesting. Again, interaction is the same thing as moderation, so we can think of this also looking back to the general linear model, the linear regression, and we looked at mediation and moderation. Moderation, you guys remember, is just another word for interaction. So interactions, moderation, these are really interesting effects that we can look at when we have more variables in our model, and they tell us something about the data, about the pattern of data, that we wouldn't be able to detect if we were to look at each of these variables by themselves. Good. So lots of good answers here. Yep. Hopefully bigger R-squared values because we have more explanatory values. So yeah, hopefully yes. Yeah, it's going to help us determine for moderation, interaction effects. I don't know, but hopefully whoever said this knows a little bit more now. So yeah, so good responses here. Helps us account for more of the variance in the data. Helps us to essentially eat away at that unexplained variance. Okay, good. So today we are going to end our lectures on ANOVA by talking about the mixed ANOVA. And the mixed ANOVA, of course, comes from the mixed design. So just like we have a between subjects or an independent ANOVA that you would use for a between subjects designs, we have the repeated measures ANOVA that you would use for those within subject designs. We have a mixed ANOVA that you will use for mixed designs. So it is really important that you think about the design from the very beginning. When I supervise students for their fourth year thesis, and whenever I start talking to them, I always ask them, okay, is this variable between, within, what is it? And a lot of people don't have a good idea. But this is one of the first things you need to clarify for yourself is, what is my design going to look like? Is my design a between subjects, fully between? Is it fully within? Is it some kind of mixed design? If it's mixed, what's between, what's within? This is really important to understand how to go about testing your hypothesis, but of course it also is really important for determining what kind of analysis you need to conduct. And so this is always a through line for all of statistics, is that the statistics you use will be based on the design of your study. If you're using a between subjects design, you're going to use some kind of between subjects analysis, whether that is an independent samplist t-test, an independent ANOVA. Right? If you're using a within subject design, then you might use a paired samplist t-test or a within subjects or repeated measures ANOVA. So you really need to be thoughtful about the design, because if you use the wrong analysis for that doesn't match your design, you're going to get invalid results, right? You're going to the data analysis validity will be broken, right? So mixed designs, you guys I'm sure are familiar, means that you have a combination of both between and within subject variables. Today's example, I'm just using one of each. Of course, you can have 3, 4, 5, as many variables as you want. Again, the more variables you add, at some point, maybe adding more variables isn't really helping you anymore. It's, usually we do maybe 2 or 3 variables in a design. But at least one of those should be between, at least one of those should be within subjects. So in this classic kind of design here, we have a pre-test, post-test, so all participants give a measurement at time 1, some kind of intervention occurs, and then we have a data being assessed again at time 2. But we have 2 different groups. One group gets the intervention, one group is a waitlist control. So we have a between subjects variable as well as the within subjects variable here. Mixed designs are really common in the research because we like to look at changes in data. So it's helpful to see, is there a change from some kind of baseline? So we know that it's not just that groups started off at different levels, and that's why we get a different level at post-test. It's really helpful to see that they start at similar levels at baseline, and we see a difference at post-test, right? So the mixed design is a really common design to use. This is one example I found from Bielowitz. I just thought this was a fun study here. And they are investigating whether there are differences between people who are omnivores, so eat like a diet of everything, versus people who are ovo-lacto-vegetarians, so vegetarian but still eat eggs and dairy, versus vegans. And they asked people to what extent do they think that various emotions are distinctly human. And so they divided these emotions up into primary and secondary emotions. So we have primary emotions would be things like, happy, fear, excitement. And then secondary emotions like guilt or jealousy or resentment, things like that. And so what they saw is that when it comes to the primary emotions, that there is no difference as a function of diet. Everybody thinks that these are not distinctly human, that animals and, humans and non-human animals, right, can both experience these types of primary emotions. But we see a very different pattern when it comes to the secondary emotions, right? Here, people who are omnivores are much more likely to say that these secondary emotions are distinctly human compared to people who are lacto-ovo-vegetarians and people who are vegans. And so what we get is a main effect of emotion. There is a difference in whether people attribute these emotions to being distinctly human or not distinctly human, based on whether they are primary or secondary. So regardless of the diet, just collapsing across the diet, there is a big difference between the primary and the secondary emotions, right? That should be obvious. The secondary emotions are much higher bars, right? We also see a main effect of diet. So regardless of whether we are looking at primary or secondary emotions, whether you are a omnivore, lacto-ovo-vegetarian, or vegan makes a difference. Doesn't matter if we're talking about primary or secondary emotions, there is a difference based on the diet. And then finally, we see a significant interaction, right? This, again, should hopefully be quite obvious. For primary, there's no difference between the diets on likelihood to attribute these emotions as being primarily or distinctly human. But for secondary, there is a difference between the different diets, right? We see that each of these groups differ significantly, or the omnivore differs significantly from the lacto-ovo-vegetarians, and omnivores differ significantly from the vegans. Vegetarians and vegans do not differ between each other. And so this is the interaction effect, right, that we wouldn't necessarily see if we were just looking at each of these main effects in separate analyses. So what we see is that, yeah, having a certain diet does seem to be related to how you feel about whether these emotions are distinctly human or not distinctly human, and it differs based on whether we're talking about these very more basic primary emotions or secondary emotions. So this is a mixed design. Diet is obviously the between subjects variable. Somebody's either an omnivore or they're vegetarian or they're vegan, but they were asked to make ratings about both primary and secondary emotions. So that's the within subjects variable. Okay, here's another example. This one is done with rats, and they looked at the number of nose pokes a rat makes. So when you have a rat and you're measuring behavior in rats, they're in a little box, and there's a little hole. They stick their nose through there in order to eat the food. So that's how we can measure their behavior, is how many times they stick their nose through the hole in order to get to the food, or water, whatever you're giving them for reinforcement. And so they looked at the learning, the ability of these rats to learn to basically stick their nose through this hole to get the food. And what they found is that there is a main effect of session. So they looked at males, females, young, and mature rats. And there's a main effect of session here. So all rats had 8 sessions, or 8 training sessions. And this is pretty obvious, right? In general, we can see that the number of times that the rats stuck their noses through the hole increases, right? So overall, we see an increase in the number of nose pokes as the number of sessions continues. Don't look at the different lines, just look at all the lines kind of together, and we can see that there's definitely an increase, right? Compared to like days 1, there's an overall increase in the number of responses being made. So this is our main effect of session. We also have a main effect of sex. So ignore whether they are adolescents or adults. Just look at the 2 circles are for females, the squares are for males. Overall, again, ignoring the days and just looking at responses for the circles versus the squares. Okay, if we collapse across everything else, it looks like overall there's a lot more circles at the top and squares at the bottom, right? Just in general, which tells us that overall females have more nose pokes, that they're learning and have a lot more responses compared to the males. We're collapsing across the age. We're not caring about age at the moment. We're not caring about the number, which trial we're looking at. We're just looking at generally. We see circles at top and squares at bottom. Circles are for females, squares are for males, which tells us that in general, females have more responses compared to the males. Now we see a sex by session interaction. What does this mean? Well, it tells us that in the beginning, there is a difference in females versus males that changes over time. So in the beginning, it's not like a huge difference, right? I think, let's see here. I can't remember exactly which parts different here, but in general, we see no real difference between the sexes, maybe around days like 4 or 5. But overall, we're seeing that, yeah, there's females have more responses across the groups here. And again, males maybe have a little bit of a difference between females on the latter days. But somewhere in the middle, there is no difference between the sexes, right? So at the beginning and at the end, we see a difference between the males and females. On those few middle days, they seem to be responding similarly. Okay, finally, age by sex by session. Now, we haven't done any kind of three-way ANOVAs in this class, but this is an example of a three-way ANOVA where we have 3 IVs. And so we can look at interactions for each of the combinations, right? So we can look at main effects of session, main effects of sex, main effects of age, which I didn't list up here because I didn't find a main effect of age. We can look at a sex by session interaction. We can look at a sex by age interaction. We can look at an age by session interaction. We can look at a sex by age by session, right? So you get all of these different combinations that you can look at. All of these can explain some amount of variance in the data. And when we look at the age by sex by session interaction, this is statistically significant as well, which tells us that in the early sessions, right, sessions 1, 2, 3, there is a difference between the adult females and the rest of the rats, right? In general, we see that adult females have higher responding in those early sessions. But in the later sessions, the adolescent females have the highest responding. So there's a difference between the males and females, but it also differs as a function of the age of those rats, whether they are adult or adolescent females. But again, it also differs as a function of which part of training are we looking at. In the beginning, adult females have the most responses. In the middle, there doesn't seem to be much of a difference. But in the end, adolescent females have the most responses. And so this is that age by sex by session interaction. Okay, any questions about how you should interpret these kinds of interaction effects? Okay, and so for today's example that we're going to use for our lecture today, we have an example coming from Zhang et al. And this is looking at differences between recalling an ordinary memory versus recalling an extraordinary memory. So this is a fun little experiment. People were divided into 2 groups. And at time 1, they were told to recall their date from Valentine's, this past Valentine's. And they were told to write about this in great detail and how amazing it was and just make it something that was quite memorable and extraordinary. Another group, so this is the between subjects variable, another group was just told to write about an ordinary day in their life. Right? So something that happened maybe a few days before February 14th. So they just wrote about something, I can't remember what the prompt was exactly, but it's just something very ordinary. Okay? So both groups were asked to write about a memory that happened recently. Now they did this at time 1, and they were asked to predict how curious they would be about this memory if they were asked about it later on, as well as how interesting they thought the memory was. They asked a few other things I didn't include in today's example, but those are the 2 big ones. How curious will you be? How interesting do you find this memory? Now, a few weeks later or a few months later, I can't exactly recall how much time passed, they went back to those same people. And they asked them to predict. They said, hey, you were in this experiment, and you wrote about a memory. And they were asked, how curious are you to reread the memory that you wrote down a few months ago? So they rated their curiosity. And then, after reading the memory, they were asked to rate how interesting they thought the memory was. So they have predicted curiosity at time 1 and how interesting they felt the memory was at time 1. Actual curiosity at time 2, as well as, again, how interesting the memory was at time 2. And so this is today's example, and I actually have the data from them, so we're going to use their actual data for today's example. But this is the results from their example. We're going to focus today on curiosity, but you can see it's pretty similar results for both curiosity and interestingness. And you can already see that, I mean, well, we'll need to go through the statistics, but you can already see that it kind of looks like there's already an interaction effect, right? Looks like there's something quite interesting happening over here. All right, so this is going to be our example for today. We have a between subjects variable, which is the type of memory that people recalled, and we have that within subjects variable, which is the time in which you made those ratings. So we'll run a mixed ANOVA since this is a mixed design, but the mixed ANOVA is really the exact same thing we've been doing for the past few weeks, right? It is an F ratio that looks at the variance that we can explain with our model, the model being those between and within subjects variables and interactions, relative to the variance that we cannot explain, relative to the variance that is unsystematic. So this is exactly the same thing we've been doing for the past several weeks, right? So test whether there is a reliable amount of variance that can be explained by our IVs and that interaction relative to the unsystematic variance. So it's just looking at variance that can be explained relative to variance that can be not explained, using our model, which now consists of between within subject variables and the interaction between these variables. And just like what we saw when we talked about the factorial between subjects ANOVA, as well as that factorial within subjects ANOVA, we will partition the variance explained by our model into the variance that can be explained by each of the main effects and variance that can be explained by the interaction. Same thing, rinse and repeat, right? Now, if we had a three-way ANOVA, so we have three IVs, same thing. It's just that now, instead of two main effects, we have three main effects. Instead of one interaction, we might have multiple interactions because we have an interaction for IV1 times IV2, IV1 times IV3, IV2 versus IV3, right? IV1, 2, and 3. So it just means that we have multiple possible interaction effects. But it's the same thing, right? So it's looking at the variance we can explain with each of the main effects, calculating an F ratio for each of those, and looking at the variance that can be explained by the interaction effects. Together, these create the variance that can be explained by your model. Any questions so far? All right, big picture. Just like what we've seen before, significant F ratio means that the model is reliable and there's a significant or a meaningful amount of variance that is systematic to the experimental treatment, right? Which means, in real terms, at least one group or one condition differs from at least one group or one other condition. Now, if you find a significant F, whether that is from your main effects or your interaction, you will need to follow those up with planned contrast or pairwise comparisons or post hocs, whichever one you want to use, to identify where that difference lies. Because just like with the one-way ANOVA that we talked about several weeks ago, the ANOVA simply tells us that there is variance that is systematic to our intervention. It doesn't tell us which group differs from which group. So we will always have to follow up any significant F ratio with those planned contrasts, with those pairwise comparisons. Okay? Okay, quick summary here. Mixed designs are composed of at least one within subjects variable, one between subjects variable, and the model includes variance explained by each of those main effects as well as those interaction effects. This variance that can be explained by a model gets compared to the variance that is unsystematic or not explained by the variables within your model, using those F ratios, exactly like we've done for the past few weeks. And then any F ratio that is significant, just follow that up with your planned contrast, post hocs, or pairwise comparisons. Same thing we've done for the few weeks. So hopefully this makes sense because it's really exactly the same, right? Okay, so we're not going to go through any kind of calculations because the concept is exactly the same as what we've talked about in the past, right? It's the same idea. If you think back to what does sums of squares model mean, it's the difference between each of the means of your model and the mean for the grand mean, right? So it's a variance we can explain. It's why we don't predict the mean of y. It's why, one group has more variant or higher scores and another group has lower scores. Sum to squares residual is the difference between what we actually observe, those data points we observe, and the mean of each group or mean of each condition. So this is always the same. So same idea here, right? Sum to squares model is the difference between what we predict with our model, so it's those group and condition means, what we predict using the grand mean. Sum to squares residual is a difference between the observed data and what we predict with our model, i.e. the group or condition means. Of course, each of these is quantity squared multiplied by, and if we're talking about the sum to squares model. So the concept is exactly the same. I'm not going to bother going through this. I just want to, just know that the idea is exactly the same. So we're just going to start going through how you would do this in SPSS. All right. I have two groups here, ordinary and extraordinary memories. Again, this is the between subjects groups variable, and we can tell because this is in one column here. And I have a within subjects variable, which is the time in which you recalled the memory, or the time in which you rated your curiosity. Time 1 or time 2. So we have ratings for curiosity, ratings for interest at time 1 and time 2. This is my within subjects variable, and again, we can tell easily because these are in separate columns. So to run a mixed ANOVA, just go back to your menu options that you've been using for the past couple weeks, go to your repeated measures, and put in the repeated measures variable that you have, which in this case is the time of recall. So we put in time. There are two levels, time 1 and time 2. Now, I've got two dependent variables, curiosity and interest. These should be analyzed in separate ANOVAs. I'm only going to analyze curiosity for today's example because the interest is exactly the same. But we have one DV that is for curiosity, one DV that is for interestingness of the memory. So you would run two separate mixed ANOVAs to look at each of these variables. So we put in the levels of our within subjects variable, predicted curiosity at time 1 and actual curiosity at time 2. Now, the only difference from last week is that we now have a between subjects factor, right? So now we're going to add in that between subjects variable, which is the group. So did you belong to the extraordinary memory group or the ordinary memory group? So just put that one in here. Otherwise, we're going to do the same thing we've done for the past few weeks. You can get some contrast if you want to. Again, you don't have to always get contrast. Think about what you would want to use the planned contrasts for. I'll be honest, I rarely use planned contrast. I use mostly those pairwise comparisons on the estimated marginal means. But sometimes if you're comparing group 1 versus groups 2 and 3 combined, then you would want to use these. So I'm showing you all the different ways in which you can assess differences between the groups. Choose the ones that make the sense for your hypothesis. Okay. So I would use, for example, the first. So maybe we'll do time and group using the first as the reference category. So time 1 as a reference category and ordinary as my reference category. Plots are always really useful. Always get plots so you can kind of just visualize what's going on. Whether you want to get line plots or bar plots is up to you. Sometimes one is easier to interpret than the other. I always, again, like to get both versions, so time by group and group by time, because sometimes it's just easier to interpret one versus the other. And so it takes you all of, half a second to put a second plot in here, so you might as well do it. Get your estimated marginal means, right? So again, these are the means that have been corrected for differences in group size as well as any covariates you might have in your design. Just gives a slightly more fair comparison. This also allows you to conduct those pairwise comparisons while correcting for multiple comparisons. So I will use the Bonferroni correction here, which is the one I always use because it's just most conservative. It's good for all occasions, basically. And then your options. So as always, just get your descriptive statistics, your effect size, homogeneity tests. So same things we've been doing every time. That's it. All right, the result's pretty similar to what we've seen before. We have, in our within subjects variable, we have T1, predicted curiosity, T2 is actual curiosity. And then in the between subjects variable, we have ordinary versus extraordinary. This tells you the ends for each of those. And then we have the means for each of these different conditions, and you can compare that to the graph to see what that looks like here. So we've already agreed. It looks like there's definitely an interaction effect. So let's follow this up and see what happens. Now, last week, we talked about the Mauchly's test of sphericity and how one of the conditions we need to assess for a repeated measures design is sphericity, which is kind of like the equivalent to homogeneity of variance, but the within subjects version, right? So it's basically saying that the variance of the differences between the pairs of your levels is the same, right? So if we do level 1 versus minus level 2, and we calculate that, and then we look at level 1 minus level 3, and we calculate those differences, and level 2 minus level 3, and calculate those differences, that the variance for each of those differences is the same, right? That's from last week. So we have a within subjects variable in this design, so of course we still need to assess for sphericity, because this is one of the requirements for a within subjects factor. We will test this using exactly the same method we did last week. We are going to look at the Mauchly's test of sphericity, and we will look at the different estimates it gives us for sphericity. Now, hold up. This is a little bit weird. It tells us that our significance is a dot, that there is a 0 for the chi-square. Everything is 1. What's happening here? Any guesses? Sorry? Yeah, why is the DF 0? I think I heard the answer over here. What did somebody said something? What did you say? There's only 2 levels. Good. We have time 1 and time 2. There's only one pair, so there can't be homogeneity of variance if we have literally one pair of different scores. Time 1 minus time 2, we get a variance. What's it equal to? There's no other difference to compare it to, right? So and this is actually exactly what we saw last week. I didn't point it out, but last week's lecture, if you see product, we were looking at the sphericity for product. That makes sense, sure. And for graphic by product, sure. But graphic has the same pattern that we see above, because graphic had only 2 levels, graphic present, graphic absent. And if you only have 2 levels, you can't assess sphericity. So in this case, we just can move on. We don't need to bother with this. So if you have only 2 levels, you don't need to worry about the sphericity, because there's nothing to be sphericity with, right? So this is why you might get a funny result like this. Okay. So don't need to worry about sphericity. Moving on, let's take a look at the results here. Now, we can assume sphericity because we only have 2 levels. So we can ignore the corrected versions. Again, remember that if we have more than 2 levels and we have violated sphericity, we have estimates for the amount of sphericity that occurs, and these estimates are multiplied by the degrees of freedom to help correct for violations of sphericity, which we can look at here. But if we have not violated sphericity, we can ignore those corrections and just look at sphericity assumed. Simplify our table a bit. So the ANOVA table looks exactly like what we've seen for the past few weeks. We've got the sums of squares. We've got your, which is the sum of the squared error, right? And this tells us the amount of variance that can be explained by your model. Degrees of freedom, mean squared, which is the sums of squares divided by the degrees of freedom. This is the average amount of variance that can be explained by your model. And then your F ratio, which is simply the mean squares model over the mean squares residual. This is no different from what we've been doing for the past few weeks, right? So we can see that for our variable of time, so there is a main effect of time. So there does seem to be some variance that is systematic to whether we're looking at time 1 or time 2. We can say that there's a time by group interaction. So there is some variance that is systematic to this interaction. So what this means is that the curiosity at time 1 versus time 2 differs as a function of whether we're thinking of an ordinary or extraordinary memory, right? And we have our error, which is being used on the denominator. So here are your within subject contrasts. We can look at time, which is level 2 versus level 1, so actual versus predicted, and then the interaction here. These you don't really need to look at so much because you already know that these are significant up here. But just like we saw up here, yes, this is significant. Now, the ANOVA is going to, the SPSS separates the between subject effects from the within subject effects, right? It's going to connect show these in different tables. So we already looked at the within subjects effects plus that interaction. Now we get our between subjects effects. So looking at time 1, looking at the ordinary versus extraordinary memories. That's the between subjects variable. If you recall from a couple of weeks ago, one of the basic assumptions of doing an independent ANOVA is that we have homogeneity of variance. The variance between our groups is roughly the same. We have a between subjects variable, so we need to check that we have homogeneity of variance here as well. And we'll do this again using that Levene's test. Just like what we saw before, we want Levene's test to be non-significant, which it is, so that's good. Now, guys, I had a question about this on the discussion board like a week or two ago about using Mauchly's test, using Levene's test, because these sometimes are not that accurate. It's true. There is a lot of critiques about Mauchly's test and Levene's test being overly conservative, right? And they will give you a significant result even though the amount of sphericity is quite small, or even though the homogeneity or the heterogeneity is quite small. That's one of the critiques. It depends a bit on sample size as well. So even if you get a significant result, that doesn't mean you're like, oh, okay, I'm done, throw this data away, right, find new data. No, you don't have to do that. One, because it gives us the corrected, we can always look at like, if you violate homogeneity, it gives us another one we can look at. If you violate sphericity, it gives us other corrected versions we can look at. But you do need to look at all of the data together, right? So if you have not violated the assumption of sphericity, not violated the assumption of homogeneity, so these p-values are above 0.05, great, move on. If you have supposedly violated these assumptions, p-values are less than 0.05. So there's a significant difference in the variance between groups, or the significant difference in the variance of the differences between the levels of your pairs of your variables. It's a terrible mouthful, right? Look at the actual data to see how big is this variance. Is it meaningful, or is this just maybe an artifact of the test being a bit overly conservative? Don't ignore the test, right? Do take it and do report it so people can, take your results with some consideration. So you don't want to ignore the test, but even if it is significant, that doesn't mean that you need to throw the data away. Do look at the rest of the results to see, is this violation something that seems to be actually worrying, or is it just a very small violation, maybe not so bad? Okay, how big is the epsilon value? Look at the variance and plot out the variance between groups. Does it look like there's a lot of variance between the groups, or is it actually quite minor, right? And that gives you a sense for how you should interpret really the significant Mauchly's test or the significant Levene's test. I'm not saying to ignore these tests. You should not be ignoring in the statistics, right? All of these results should be looked at together to give you an overall picture for what's going on in your data. But even if you get a significant Mauchly's test or a significant Levene's test, you can still continue with your analyses by looking at the rest of the results and giving some context to what that significant result might actually mean. Okay, so Levene's test, though, in this case is not significant, so hooray, do you even have to think about that? You just move on. And we are looking at the test of between subject effects here, and it looks like there is not a significant difference between the groups. So whether your recalling whether you're making ratings about an ordinary or extraordinary memory, there is not a difference in curiosity. But again, overall, this is collapsing across that within subjects variable. This is just looking at the ratings for ordinary versus the ratings for extraordinary. And we're not thinking about whether it's done at time 1 or time 2. We're collapsing across that variable. This is just looking at the between subjects main effect. And when we do that, we see that there is not a significant difference between our groups. That's not so interesting, though, because we already know that there is a significant interaction, which was interesting. Now, we can look at the planned contrast we asked for. This is looking at extraordinary versus ordinary. And here, the hypothesized value is equal to 0. So we would, in the null hypothesis, predict that there is no difference in curiosity ratings between extraordinary memories versus ordinary memories. That's what the null hypothesis says, right? The null hypothesis is always no difference, no effect, no relationship. So we hypothesized a difference of 0. We observed a difference of 0.195. So the difference between what we observed and what we hypothesized is 0.195, right? The standard error is 0.205, and the difference between observed and hypothesized is not significant. So effectively, there is not a difference between curiosity ratings for extraordinary versus ordinary memories. All right, so this is your planned contrast here. Let's take a look at those estimated marginal means. So the grand mean, ignoring all conditions, all grouping variables, the overall rating for curiosity is 4.160. Now, if we look at the pairwise comparison, there it is. Look at pairwise comparisons. Comparing ordinary versus extraordinary, again, we've already kind of seen that this is not significant, and indeed that is correct, right? The difference between ordinary and extraordinary is 0.195. This difference is not significant. So when we collapse across that within subjects variable, there is not a difference between the ratings for ordinary versus extraordinary memories. What about the within subjects variable time? Our ANOVA table already told us that this is significant. We had a main effect of time. We only have 2 levels, so we already know that this is going to be significant. And indeed, looking at time 1 versus time 2, the difference in curiosity ratings is 0.343, and this is significant. Now, this is collapsing across the group variable. So it doesn't matter if we're looking at ordinary or extraordinary memories. The ratings at time 1 differ significantly from the ratings at time 2 overall. Kind of interesting, but honestly, these main effects are not really what we're interested in. What we're really interested in is that interaction effect. Do we see a difference in curiosity between ordinary and extraordinary memories based on the time in which these ratings were given? That's what's really more interesting, right? And indeed, we do. We see that at time 1, there is a difference between the extraordinary and ordinary memories. So at time 1, ordinary memories are rated as being less curious compared to extraordinaries. So people think that they will be not very curious or less curious about rereading an ordinary memory in the future than they would about an extraordinary memory. But at time 2, this difference is not significantly different. So at time 2, the curiosity ratings for ordinary and extraordinary are both quite high. So at time 2, everybody's curious about the memories. It doesn't matter if we're talking about ordinary or extraordinary memories. Everybody's curious about the memory that they wrote down. Now, we can look at this in the other direction. Same results, just giving it to you again, both directions. So if we look at the ordinary memories, what we see is that at time 1, there's a difference between the curiosity ratings for ordinary memories at time 1 and time 2, right? So at time 1, we see a lot lower ratings of predicted curiosity versus actual ratings of curiosity at time 2. But this difference is not significant for extraordinary memories where curiosity ratings are high at both time 1 and time 2. Again, this is the same result, just given to you the other way, based on the hypothesis you have made and the way you phrased your hypothesis. One of these may be more relevant than the other. So that's it, right? That's all there is to it. Conclusion, participants' curiosity in an extraordinary memory does not change based on the time in which they make this rating, but participants' ratings of ordinary memories does change. Initially, when they write down this memory, they think that they're not going to be interested to read it again. They're not going to be curious to read it again. But, a few months later, they're actually quite curious about the memory that they wrote down. Okay, so when you use the mixed ANOVA, use it when you have a continuous dependent variable, right? So one continuous DV, two or more categorical IVs, at least one of which is between subjects, at least one of which is within subjects. You've met all the basic assumptions for those parametric analyses, including the assumption of homogeneity of variance for that between subjects variable and the assumption of sphericity for that within subjects variable. Now, if you have violated the assumptions, you can always check if you have any outliers. You could maybe remove some outliers. You can always maybe try to transform your data. You can maybe use just a more conservative alpha value. There's not a good non-parametric version of a mixed ANOVA. So if you have violated the assumptions in some major way, you might want to just rethink the analysis altogether. But there's not an easy non-parametric version for this. Now, quick word break from here. This reminds me, I made an announcement about this on Canvas, but just in case you guys didn't see the announcement, it came to my attention that many of you did not learn how to do the assumption testing in SPSS. You guys learned about assumption testing, but not necessarily how to do it specifically in SPSS in 2131. That's fine. For your group projects, you need to still think about the assumption testing. You don't need to do them in SPSS, although your analyses will be done in SPSS, but you need to tell me what are the assumptions that you should be testing for this analysis. What should you be looking for in terms of, you're looking for p-values of less than 0.05, or you're looking for, I don't know, residual errors that are going to be relatively normally distributed, or whatever it might be. What are you looking for to test the assumptions? And what would you do if you violate those assumptions? You don't actually have to run those assumption tests in SPSS, but you need to tell me what assumptions you should be testing, why you should be testing those, what you're looking for to assess that the assumptions have been met, just in general, okay? Okay. To write up your results, same thing as we've talked about for the past few weeks, right? Include the statistic, degrees of freedom, p-value, effect size, any kind of plan contrast, pairwise comparisons, or post hocs. Graphs and tables of the descriptive statistics are always helpful. So if you write up your results, same questions as I've been giving you guys for the past few weeks that you should ask yourself and to think about as you write up a results section. Importantly, guys, I want to just emphasize this over and over again. When you talk about the results, don't just refer to a table. Don't just write numbers. You need to interpret what those numbers mean. You cannot just, say, there is the result, here are the numbers, and this is significant, and move on. What does this mean? Bring it back to your variables. Bring it back to your hypothesis, okay? A monkey can sit there and type out the same numbers that it sees on a screen, and if it sees that the little p-value is less than 0.5, it can write the word significant and not significant. Do more than a monkey can, all right? Tell me what this means if the result is significant. What does it mean? Which group has faster reaction times than which other group? What does this mean in terms of the effect of your manipulation? Whatever it might be. So interpret the results. Don't just copy paste from the table in SPSS to a table in Word, okay? Okay, so here's an example of a results section that I would write up here. Again, you don't have to copy what I do word for word, but this just gives you an example for the kinds of information you should be including, right? But again, this is just answering the same questions as I have listed here, okay? Again, your textbook has a nice flow chart that you guys can follow if you get a little bit lost on what to do in terms of doing a mixed ANOVA. It's helpful to look at. Okay, quick summary here. SPSS separates within subject effects and interactions from those effects that are strictly between subjects. So you get different tables. And use your pairwise comparisons and your plan, contrast, post hocs, whatever you need to test for differences if you get any kind of significant main effect or any kind of significant interaction. Do check those assumptions. So use that Mauchly's test to check for sphericity, use the Levine's test to check for homogeneity variance, and write up all the results. Make sure to include pertinent information. Make sure that you're relating this back to your original variables. Any questions? Yes. Yeah, good question. So if the results are not significant, what do you do? Okay, so you should have laid out in the very beginning what tests you will be conducting anyway. So you need to talk about what are the analyses you will conduct. So we're going to, based on the hypotheses we're testing, we're going to conduct a mixed ANOVA and to test whether there is an effect of, type of music on word recall, we're going to compare this group versus this group, right? So you're kind of already laying out the pairwise comparisons you would be assessing, you would be checking to test those specific hypotheses. So that really kind of comes more at the beginning, at the introduction or the methods section, right? If you don't get significant effects, then yeah, you don't need to look at those pairwise comparisons for the results. But you should have laid out somewhere in the beginning, either in the end of your introduction or in the methods where you talk about the plan analyses. You should be laying out there which analyses you're going to conduct and what you're going to compare to test your specific hypotheses. So your grader, i.e. your tutor, knows that you know what you should be looking at, right, and how you would be testing those. So we would test those using plan and contrast to compare this group versus the 4 other groups, or we would be using pairwise comparisons to test all these different groups using the Bonferroni correction or whatever it might be, right? So you should be laying out exactly what you're going to do in the plan analyses. But yeah, if the results are significant, then the actual results, you may not discuss that then later. Good. Other questions? Okay, so we're going to end our lecture by doing a bit of a review to bring all of these different topics from the past few weeks back together. So just linking everything up. General linear model, big picture, guys. Because everything we've been talking about for the past few weeks are just types of general linear models. All the same thing, just slight variations of the same basic idea. So, general linear model, we started talking about this back in week, 7-ish, I think, when we started talking about like linear regression. So, general linear model is a statistical framework that describes how a continuous DV is related to a set of predictors, categorical or continuous. That's the basic idea of a general linear model. How do these variables relate to my outcome variable? Okay. Now, in linear regression, t-test, ANOVA, these are all just types of general linear models. They can all be boiled down to the simple model of the outcome is equal to the y-intercept plus the value of your variable and the way that that variable is related to the outcome. So the slope, right? This is the basic format for all of these general linear models. If we have a continuous predictor, and we're talking about linear regression, then the y is the DV being predicted. B0 is your empty model. This is the y-intercept. So this is when the variable x is equal to 0. Right? So if you think about where it crosses the y-axis, x is literally equal to 0. So this is the value we predict for y when x is equal to 0. Again, thinking back to my example, when you go to the theme park, before you buy anything in the theme park, there's an entry fee. So that's how much it's going to cost you. And anything beyond that, whether you buy food, whether you buy drinks, whatever, right, that's additional costs. But there's a starting point. When everything's equal to 0, this is the starting point of how much it's going to cost you. And then this is the relationship between x and y. Okay, so the correlation. So if we want to predict y, the value of y, this is the model we're using to predict it. Categorical variable is exactly the same. The only difference is that the B1 is the difference between the means. So if we dummy code our variable, our categorical variable, into 1 and 0, B0 is equal to the mean of the group that is categorized as 0. B1 is the difference between the mean of group 1 minus the mean of group 0. It's the difference between the means. Right? So if we were to think of this in a plot, you think of the two groups, right? You've got a group 0 and you've got group 1. There's a mean for group 0 and mean for group 1. If you were to draw a line between the mean for group 0 and the mean for group 1, that's also the slope. So this is the slope. This is the difference between the means. If there's a big difference between the means, then the slope is going to be steeper. If the two means for your groups are roughly the same, the slope is going to be very flat. And just like with a continuous variable, the steeper the slope is, the more likely it is to be significant. The flatter the slope is, the less likely it is to be significant. Same idea here. If we have one predictor, right, we can have variable x, whatever the variable might be, so whatever the value that is. So this could be the number of hours you spend studying. This could be the number of meals you buy at a theme park. This could be the, I don't know, whatever, your anxiety rating, right? This is the relationship between your predictor and the outcome variable. So to what extent is the number of hours you spend studying related to the grade on your final exam? How is anxiety related to, let's just say, loneliness, right? How are the number of meals related to how much you're going to pay for a day at the theme park? So this is the relationship between x and y, and this is the empty model when x is equal to 0. If we have one predictor with two levels, we're doing a t-test, right? So if we have one predictor that's continuous, we're just doing a simple linear regression. We might have group experimental, so this gets coded as group 1, and group control gets coded as group 0. So this is the mean for group experimental. This is the mean for group control. This is the difference between group experimental's mean minus group control's mean. Again, this is simply the difference between the means of your groups. If you were to draw a line between these two means on a graph, this gives you a slope that shows you the how steep the difference is, or the difference between the two means. The t-test is simply a test of the difference between the two means, experimental minus control, over the standard error. So if we do a linear regression and we are doing a t-test, we're looking at the slope, right? The t-test is looking at whether the slope for each predictor is significantly different from 0. Is the slope flat, or is it, slanted in some way? And again, if you think about a categorical variable and you draw a line between these two means, this gives you a slope. If the slope is flat, the t-test is going to be not significant. If the slope is not flat, then the t-test should be more likely to be significant. Same thing. Maybe we have multiple predictors. Same pattern. Now we have another predictor which has its own relationship with the outcome variable. So we have the empty model when both of our predictors are equal to 0. We have predictor value for predictor 1 and the relationship between predictor 1 and the outcome. Value for predictor 2 and the relationship between predictor 2 and the outcome. And our model is looking at the combined ability for predictor 1 and predictor 2 to be related to the outcome. So it's the joint relationship between predictor 1 and predictor 2 with the outcome. Maybe we have one predictor with multiple levels, but it's a categorical variable. So instead of 2 levels like we did with the t-test, now we have 3 or more levels. So we're going to run an ANOVA. Right? If you recall, the t-test for an ANOVA, B0 is the mean of your control group. This is the mean, or this is the group 1, and this is the difference between the 2 means. Same thing for a one-way ANOVA. B0 is your control group. X1 is group 1, whatever you want to call this. Maybe this is group high. And then B1 is the difference between this group minus the control group. So it's the difference between group high minus group control. But we have another group. Maybe it's called group low. So group low gets coded as also 1 because we've dummy coded these things. And B2 is equal to the difference between group low and group control. So it's the difference between that experimental group and the control group. These together create your model. Okay? We can do even a multiple linear regression that has both categorical and continuous variables. So we just tack on another variable here. We have a third variable that gets dummy coded. And just like what we saw over here with our one-way ANOVA and our t-test, B3 is the difference between the experimental group and the mean of the control group. And then we can have a factorial independent ANOVA. Again, it's the same thing, right? So we have the, where's my thing? There. This is the mean of your reference group. This is the one that gets zeros across everything. So it's considered, low and neutral. So it's coded as 0 for factor 1, which is low, high, and control, or low and high, I guess. So we've got two levels, low and high. So low is group 0, high is group 1. And we've got second factor, which is positive versus neutral. So this is the group that gets both low and neutral. This is coded as group 0, 0. Your reference group. Then we have variable 1. So factor 1, which is the group high. Now it's still neutral because we're only looking at this one factor, group high. And B1 is the difference between group high versus group low when both of these are coded at neutral. B2, this is our second variable, so this is going to be positive. So this is positive minus neutral when both of them are coded at low. And then we have our interaction term. How do these variables interact together? So we have B2, which is when we have both high and positive. So this is when it's coded at 1 and 1. And then we have the interaction term, which is a little bit harder to understand. I worked it out. Somebody asked a question about this on the discussion forum, and I worked it out step by step on the discussion forum. So you can see that there. But it's also worked out step by step in your textbook. But this is the difference between being in group high when you're neutral versus group low and neutral, plus the difference between being in group positive when you're being in group high when you're positive and low when you're positive. All right, but it's the same pattern. Each of the coefficients, the B1, B2, B3, is the way in which that variable relates to the reference category. Okay? And then we talked about the repeated measures ANOVA. Slightly different format, but overall same idea. We have the grand mean, right? So this is like your empty model where we're not thinking about the predictors. This is the subject effect. So this is the individual differences that we don't usually care about when we're doing our ANOVA, but it is something to consider if we're trying to predict the overall value of y. So what are the individual differences we have between participants? What is the effect of our within subjects treatment? So what are the differences that we see within participants going from level 1 to level 2 to level 3, as that is systematic to our treatment? And what are the differences we have within participants, but between treatments, that is residual noise? Okay? So the general linear model can be applied to all of these different types of analyses we've been talking about. It's the same general pattern where we're trying to predict an outcome as a function of a set of variables or predictors, and how each of those predictors is related to the outcome. That's the general linear model. We conduct an ANOVA to determine whether our model is reliable. Is it significant, statistically significant? Is there variance in the model that can reliably explain what's going, or that is reliably systematic to our model, to our predictors? Okay? And we will calculate this ANOVA by doing an F ratio that looks at the variance in the data that is systematic to our model and compare this to the variance in the data that is not systematic to our model. And it's the same thing over and over and over again. If we've got a linear regression, it's the variance that is systematic to the joint correlation between all of our predictors and the outcome variable. That's systematic, right? So if I'm looking at the effect of, or if I'm trying to predict your exam grade as a function of the number of hours you study and how much you're interested in this subject, then assuming that both of these are positively correlated to exam grade, I can explain why people who are both more interested in this subject and people who study more get higher grades than people who are not interested in this subject, who are not studying as much, right? So there's variance that is systematic to the way which these variables are related to my outcome variable. So that's variance that is explained based on my model. I cannot explain why people who have the exact same level of interest and have studied the exact same amount still get different scores on the final exam. That's due to stuff that I didn't include in my model. So that's the residual variance. Okay. Likewise, when I talk about, so in a linear regression, it's the correlation between the predictor and the criterion variable. So the sums of squares model is the variance that can be explained by that relationship between my predictors and my outcome variable. This gets compared to that residual variance, right? Why people with the exact same scores of interest in studying get different scores on the exam, don't know. That's my residual variance. And the F ratio is just compares these two levels of these two sources of variance. A significant F ratio means that there is a reliable amount of variance in the data that is systematic and that can be explained by my model. Oops. So we conduct an F ratio using the average amount of variance that can be explained. Oh, there's my middle. Average amount of variance that can be explained over the average amount of variance that is unexplained. And these mean squares, literally, when I say mean squared, meaning average, right? It's the mean squared is simply the average of the sums of squares. So it's taking the sums of squares and divided by the degrees of freedom, which gives me an average. So is the average amount of variance that I can explain more than the average amount of variance that I cannot explain? That's basically what the F ratio is looking at. Now I can do the same thing with categorical variables on my ANOVA. Here, the model in my ANOVA is the means of my groups or means of my conditions. And maybe I am investigating whether there is a difference in, let's just say, people's loneliness. And I'm looking at whether people are living with other people or not living with other people. And I'm looking at whether people tend to have, let's say, some kind of chronic illness or no chronic illness. So I'm using these two variables to help me predict whether people are going to their level of loneliness. Okay. And so I might be able to explain, assuming these variables are significantly related to loneliness, why people who live alone And people who have chronic illnesses have higher amounts of loneliness compared to people who live with others and people who do not have chronic illnesses, who have lower levels of loneliness. So that's some variance I can explain, right? And so I would expect there to be some variance that is systematic to these different groups. So my means are the model that I'm using, and I would expect there to be some variance that is systematic to the different group assignments or my interventions or treatments. The variance I cannot explain is that residual variance. I don't know why people who live with other people and do not have chronic illnesses, some people might still be very lonely. Maybe people who live alone but have chronic illnesses, some of those people might be lonely, some of them might not be lonely. So there's some variance within each of these conditions that I cannot explain. That's my residual variance. Same thing for the within subjects ANOVA, right? So that was a between subjects design. I can have the exact same concept for the within subjects design. If I'm looking at the predicting your, let's just say, how much you like somebody after the number of times you meet with them. So maybe this is a thing where you meet with a group. Maybe you're coming to a group the first time versus the second time you meet them versus the third time you're meeting them. And I'm looking at whether this person is a male or female that you're meeting. So how much do you like being around this person? Based on how much exposure you've had to this person and whether that person is a male or female. Okay? And you meet with both men and women. You meet everybody 3 times. And I'm rating how much you like this person. So it's a fully within subject design. Everybody meets 2 people, a man and a woman. Everybody meets these people on 3 occasions. There is going to be some amount of variance, I would hope, that is systematic to my treatment effect. The number of times you meet people should hopefully increase how much you like that person. And maybe there's some variance based on whether it's a man or a woman, I don't know. But there's maybe some variance that is systematic to my treatment effect. There's going to be some variance that is not systematic to my treatment effect that I can't explain, right? Maybe, in general, I see that people's ratings of liking increase with increasing exposure to this person. But not everybody's liking increases, right? There's some people who maybe their liking of this person decreases as they have to spend more time with them, right? That's variance I can't really explain. So my ANOVA is going to look at the variance between these conditions, or the variance that is within my participants, but at different levels on my within subjects condition, that is systematic to the treatment, versus variance that is within my participants, but within each condition, that is unsystematic. So it's the same idea as the independent subjects ANOVA. Variance, and in the independent ANOVA, it's variance between groups, because that is how we're differentiating our conditions, or our treatment effect, versus variance within groups, because each group gets a different treatment. When we talk about a within subjects ANOVA, it's variance between conditions, because everybody goes through multiple conditions, and we expect there to be differences in people's behavior as a function of which condition they are in, relative to variance within each condition, right? There's some amount of variance within each condition that we cannot explain. But it's the same idea. And the ANOVA is going to compare the variance that we can explain, that is systematic to our intervention, our treatment, relative to the variance we cannot explain. So it's variance that is systematic to our model. So it's the difference, the square, oops, I forgot to add the square here. Pretend that there's a little square here. So it's a squared error between the mean of our model minus the grand mean multiplied by the n, quantity squared. That's the sum of squares model. And then the residual variance is the difference between what we observe and what we predict with our model. These are exactly the same, right? So if we think about linear regression, the sum of squares residual is the difference between what we observe and what we predict with our model, right? We cannot explain why people who study a lot still get low grades. That's residual variance. We cannot explain why people who live with others are still lonely. That's residual variance. And the ANOVA is simply going to look at the average amount of variance we can explain with our model relative to the average amount of variance we cannot explain with our model. So it's the same thing over and over and over again. Okay. So to summarize, general linear model is the basis for linear regression and the ANOVA. Coefficients for each term represent the relationship between the predictor and the basic model or the reference group, right? Depending on if we're talking about categorical or continuous variables. Thus, they're either the correlation between the predictor and the criterion for a continuous predictor, or it's the difference between the mean of the predictor X and the mean for the reference group if we're talking about a categorical variable. Now, assess the reliability of the model by comparing the variance explained by the model, which is your sums of squares model, to the variance that is not explained by the model, which is your sums of squares residual. And assess the goodness of fit of the model by calculating that R squared. So do check the effect size, or partial eta squared if you're doing ANOVA. And a significant F means that the variance explained by the model is reliable, and using the model to predict a score of Y is more accurate than just using that basic model alone. In ANOVA, it basically just means that there's a difference between at least two of your groups or two of your conditions. Any questions? Okay, so quick summary here. The general linear model is the basis for the regression analysis in the ANOVA. ANOVA is a ratio of variance explained by the model relative to variance not explained. Significant F means that there is a reliable amount of variance that's systematic to the model. Mixed ANOVA is used for mixed designs and analyze main effects and interactions, just like you've done for previous ANOVAs. Okay. This is all covered in chapter 15 of your textbook, so you can read up more there. If you still have additional questions, you can also ask questions on the discussion forum, or you can make an appointment with me during my office hours. As usual, they are Wednesdays from 9:30 to 12. You can sign up on campus. Okay, so we'll end with the quiz yourself. So you can go back to the quiz yourself link here. Okay, so what can produce unsystematic variability? Now, you can choose more than one answer here, and the correct answers are all but the experimental manipulation. So what can produce unsystematic variability? Individual differences, right? That can certainly produce some variability that is not systematic to our treatment effect. What else? Extraneous variables, right? That can also produce unsystematic variability that can account for differences between our participants that we just can't explain. And even questionnaires with low reliability. If you're using a questionnaire that is not reliable, that means that the way that people respond to it will be inconsistent, which means that you're going to have a lot of variance that is just unsystematic. That's why when we talked at the beginning of the semester about reliability and validity, it's so important that you do think about the reliability and validity of your designs, but also of the tools you are using, because if you use tools that have low reliability or low validity, that will impact the overall results of your analysis. Good. Next question. So, what are some things that will produce systematic variability in the data? Okay, yeah, good. Very good. So, your manipulation will hopefully produce some kind of systematic variability. That is what we're aiming for. And then if you have a correlation, right, if you're talking about a linear regression, if there is a correlation between your predictor and the outcome variable, that's hopefully also going to account for some systematic variability in the data. Good. All right, does adding more factors to your model always increase the explanatory power of your model? Yes or no? Correct answer here is no. Again, think back to what we talked about at the very beginning of the class. If you add variables that are not significantly related to the outcome variable, then it's not going to increase the explanatory power of your model. So do be mindful of which variables you add and which variables are perhaps just not very useful to you. Good. What are main effects? All right, correct answer here is yes, A, the effect of one variable on the DV while collapsing or ignoring the groupings of other variables. So it's when we ignore any other variable, and we're just looking at the effect of one of the variables. All right? Good. What are interaction effects? All right, yes, correct answer is B, the differential effect of one factor on the dV at varying levels of another factor or factors, right? So it's the difference in, how people feel about primary versus secondary emotions and whether these are uniquely human as a function of whether you are an omnivore, vegetarian, or vegan, right? It is the level of curiosity that you have about a memory at time 1 and time 2 based on whether that memory is extraordinary or ordinary. So it is the effect of one variable on the outcome that differs at varying levels of another factor or factors. Good. Okay. When should you conduct t-tests, blend contrast, post-hocs, or pairwise comparisons? Okay, yes, good. Everything except for the last. If you get a significant F ratio, you should always be following this up, right? The F ratio doesn't tell you what differs from what. It doesn't tell you which predictor is a significant contributor to your linear model. It doesn't tell you which condition differs from which condition. Always follow this up with your post-hoc tests. Okay, final question, which we're running out of time here, but when should you conduct a linear regression analysis? When should you conduct an ANOVA? Okay, so, ANOVA is checking for interactions, linears. So it's here, continuous versus categorical, multiple levels here. Okay. Yeah, this is really the answer I'm looking for here, right? Linear regression is testing for the correlation between a predictor and the outcome. It's looking at whether a certain variable or set of predictors is related to the outcome using that correlation. Generally, when we do ANOVA, we're looking for differences between means. So an ANOVA is really about looking for differences, whereas the linear regression is looking for that relationship based on the correlation. Now, a linear regression can be used for categorical and continuous variables. If you have continuous variables, you cannot do a ANOVA, but we can analyze this using the linear regression and using that general linear model. Now, ultimately, these are both just types of GLM. So they can, in some sense, be a little bit interchangeable in terms of sometimes, based on what you're hypothesizing, you might use one versus the other. But by and large, linear regression is based on the correlation. You can use categorical and continuous predictors. ANOVA is looking for differences between groups, differences between conditions, and this is using only categorical predictors. Now, if this was you who said, I don't know, crying, please sign up for my office hours and let's make an appointment. I've been meeting with other students every week, and I'm very happy to meet with you as well and spend as much time as you need. So if you guys have questions, if you're still unsure about things, do sign up for my office hours. Okay, now, last thing, there is a your turn, so you can go back to the data and try to analyze the concussion data again using that mixed ANOVA, looking at the trial effect by the grouping of age and number of concussions. That's it, guys. Next week, we still have class, so do come prepared with any questions you have for next week. Okay, bye-bye.